In an era where any factual answer is a click away, the value of rote memorization has effectively vanished. Success in the modern world is no longer defined by what a student can remember, but by what they can do with that information. Navigating the current information landscape requires higher-order thinking skills. Students must be capable of reasoning through complex data and applying creative logic to solve problems that don't have a pre-written answer key. However, teaching abstract traits like flexibility or originality is difficult within the rigid structure of a hard science class. Standard lab experiments are often designed to produce one specific predetermined result, leaving little room for independent thought. To bridge this gap, education models must force students to apply scientific theory to messy, real-world challenges that require immediate, tangible solutions. This practical application is exactly what occurred at SMA Negeri 1 Weleri, a high school in Kendal, Indonesia. During a chemistry lesson on colloidal materials, the students began discussing the local urgency of COVID-19 prevention, highlighting a critical shortage of hygiene products in their community. The students recognized that the chemical concepts they were studying provided the specific mechanisms needed to address the health crisis in their own neighborhoods. The classroom adopted an Ethno-STEM Project-Based Learning framework. This model integrates local herbal knowledge with rigorous scientific synthesis and engineering principles. The goal was to develop an effective herbal soap that combined Indonesia's cultural botanical heritage with global standards for chemical safety and efficacy. The project began with an exploratory phase. Students formed groups to research the specific chemical requirements for soap making alongside the cultural history of medicinal herbs. This research utilized the technology aspect of STEM, with teams using the internet to source materials and computers to catalog and organize their chemical data. Next came the mathematical requirements. To ensure a successful chemical reaction, the students had to calculate the exact mass and composition of each reagent involved in the process. The math extended to the business side of the project as well. Teams had to plan a production budget and perform a profit and loss analysis to ensure their products were economically viable. Before beginning the physical work, the groups presented their designs to their teacher for feedback, refining their chemical procedures and safety protocols. By prioritizing data and budgets over immediate labor, the students followed a professional engineering workflow, one where physical creation only begins once the variables are fully controlled. With their blueprints finalized, the students moved into the physical lab to begin the process of synthesizing their specific soap designs. This process is driven by saponification, a chemical reaction where local fats or oils are exposed to a base, causing the molecules to restructure into a colloidal substance. The ethno component comes from the students' use of traditional Indonesian herbal knowledge, infusing the soap with local plants known for their medicinal properties and distinctive aromas. The engineering phase followed, as teams designed the physical shape, branding, and packaging to ensure the product was both functional and culturally relevant. Every batch underwent quality control testing. Students evaluated their soaps for hand-washing efficacy, skin softness, and olfactory appeal. This phase transformed the abstract formulas of a chemistry textbook into a finished product designed to solve a specific community need. The project concluded with a final evaluation. Students presented their finished soaps and their experimental findings to the class and a panel of evaluators. During a formal Q&A, the teams had to use their experimental data to defend their engineering choices and justify their chemical compositions. This defense reinforced communication as a vital STEM skill, requiring students to translate their technical work into a persuasive, evidence-based argument. To measure the impact of this approach, a 2021 study by Ariyatun analyzed the cognitive development of the students throughout the soap-making project. This chart displays the primary results. The majority of the students reached the good category for both critical and creative thinking. Within the critical thinking metrics, the students showed the highest proficiency in providing simple, logical scientific explanations, reaching a score of nearly 79%. On the creative side, the students excelled in flexibility, measured at over 80%. This demonstrates their ability to generate alternative ideas and pit during lab failures, skills also reflected in their high scores for fluency and elaboration. By integrating local cultural wisdom with rigorous STEM standards, the classroom produces more than just a functional product. It provides students with a measurable increase in their ability to innovate.